We'll continue now with question 4 on the 2017 final exam. We've done part A where we created an encoder, and in this case we're starting with a new encoder. So we're given the trellis diagram. So the trellis diagram is here. So here are the code words again on the assignment, but now everything is filled out. It's not like the last one where I had to fill everything out. And of course, if we look at each one of the rails, we will see again that there is basically one code, 1010, and it's the first bit that determines why they're on the two rails, the difference between the upper rail and the lower rail on the same transition. For instance, the transition from A to B, I have the 0, 1 is the difference between the lower and the two sides of this rail. Okay, so that's what we saw previously. Now what we change in this part of the problem is that we're telling ourselves, or we're giving the information on which modulation system is being used for the transmission. And in this case, the modulation system is 8-QAM. So we have 8-QAM. And 8-QAM, of course there are many different possibilities for 8-QAM. In this case it's rectangular 8-QAM because we see the constellation which is provided here. And in the constellation we're giving a label for each symbol. For instance, this symbol is called symbol A. This symbol is called symbol E. So we just give names to them so we can tell them apart. And of course there's also a bit to symbol mapping for TCM. And in this case, the bit to symbol mapping is also given. So there are 3 bits next to the name for each symbol. And those correspond to the bits that are associated with each one of these transmissions. So in this case, in our trellis encoder, we've done something a little different because in addition to given the bit sequence, the code word, the 3-bit code word, on each one of the transitions, we give you a little bit more information and say, well, that 0000 for this 8-QAM constellation is in position symbol A. So you can look at the correspondence here, and of course when I have the letter G here, it's because if I look at the letter G, it's the 110 code. So every time I have a code 001, I look up, oh, 001, that's B, so we wrote the B next to it. So it's the same operation of what we did in the previous part of the problem, but in the previous part we only wrote the code word. Now we know which modulation format we're going to use, and so we just put next to it the symbol position. And the reason we do that is because we're going to be using Euclidean distances, and it's a little, we're not using Hamming distances. So we're using Euclidean distance. When we use a Hamming distance, then having the bits is good enough. We can do all of our calculations on our metrics in the trellis. But when we're doing a Euclidean distance, then we really need the IQ coordinates. And if I have just the bits, I don't know what IQ coordinates there are. But when I write, for example, the letter A, then I know I can look here and find what are the coordinates, the IQ coordinates for this system. So using those coordinates is what is involved in the second part of the problem. So I'm really just setting this up for you. Now the next part of the problem is you're actually going to have to compute some Euclidean distances. So for the Euclidean distances, you're asked to compute 2 different ones. And we're looking, in fact, for the minimum distance. And so you're given that this exercise is all about finding Euclidean distances and finding minimum distance for this particular code which we're provided. So for the code that's provided, we're given the task of computing 2 different distances. Here you see is one already highlighted path where I go from state A, then I go to state B, that's the first one. Then the second part I go from B to C, that's the second part here. And the third part, I go from C back up to A. So I go, if I were going to write this transition, I would say it was A to B, B to C, and C back up to A. And of course, when we're looking for minimal distance, we're always going from A to A. We're looking for paths that go from A to A. And if we're going to be comparing the length of this path to the length of the all zero path. If I go down to the second part of the problem here, of course we have the transitions now are A to B. That's the first one here. And then we're going from B to D. And from D, I go back up to C. And from C, I go back up to A. So this, of course, also goes from A to A. There are more steps in this path, but that doesn't necessarily mean it's longer or shorter, because this distance we were really interested in is, of course, the Euclidean distance. And it doesn't have to do with how many hops, how many segments there are, but it has to do with the difference between the code words distances between the path we're examining and the all zero path here. So we're comparing those two distances. For this exercise, we're using very simple coordinates, 1, 3, minus 1, minus 3. So we're using IQ space for this calculation instead of signal space. And this is like the example that was done in class, so we kept it the same as the example in class, but of course we could have done this in signal space and maybe it would have been a little more straightforward. But in any case, of course, if we only used QPSK, it would have been these inner 4 coordinates, and then it would only have been B, C, G, and F. And there's 2 distances, and the shortest distance is, of course, between B and C, which is 2 in this case. And of course, that it's not written here, but that's the same as the distance between C and F, between F and G, and between B and G. But the only other distance that's provided is B to F, so this diagonal distance, which is 2.83, and it's not written, but of course it's the same as the CG distance. So the minimal distance in this case, you look at the 2 distinct distances in QPSK, the minimum distance would have been 2 in this case. So it's important to know the Dmin and the average energy per symbol, because those are what you use to compare the performance of the 2 systems. So this is the classic QPSK in IQ coordinates, classic result. So now we look at the 8QAM case, and in the 8QAM case, there are 4 distances which are of interest. Those are the dotted lines here. So there's one distance between A and B. Of course, it's the same as the distance between C and D, between D and E, between E and F. All those distances are the same. But it says A and H, but that's just an example. It really covers all of those sort of single right angles on the distances. So that clearly is the same calculation that we made in the other IQ and the in the QPSK. And so for that length there, the distance is 2. So there are 3 other unique distances. One of them is the cross distance, like from A to G. That was 2.83. Just again, like we found before, it's the same. And of course, it applies to all of these x's that I'm drawing. All of these are at the same distance of 2.83. So we've covered 2 of these distances. So we've covered 2 of these distances. We've done that one, we've done that one. And now let's look at the next one. And the next distance of interest is from A to F. A to F is length 4.47. And of course, you could find a couple others which would like that, like B to E would also be at that distance, C to H, and D to G. So again, the idea is that I'm giving you the numbers here for your calculation for all of the possible distances. So you won't have to do that during the time allotted for the exam. And there's one other distance that remained, the really extreme distance from A to E, and of course that would be the same as D to H, and that one is given as 6.32. So clearly, we can see all of the necessary calculations that will be involved in doing finding the minimal distance for this code. So remember, minimum distance for the Trellis coded modulation is not the same as the QPSK. And QPSK, you know, we looked at these two distances. We said the smallest of it was 2. That became our d-min. And now with our average energy per symbol, we'll be able to look at the performance of that code. But we don't do the same thing here. We don't look at these 4 and say, oh, the minimum distance is 2. No, 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 not at all. Because now we have coding. And when we have coding, the minimum distance is determined by a path. So we have to look at the path to find out what the minimum distance is for this code. And that is what part B is all about, is finding the minimum distance for this code. So we have 2 paths, and we have to compare the distances between each one of the metrics. So we're going to look, for instance, here there's a distance between these two, and how are we going to find it? So we're going to look back at our trellis here, and of course we know that there's either an A or an F associated with this. So I'm going to put A, F. Those are the 2 transitions for that point there on that rail. And now if I look going from A to B, there's either D or G are the 2 possibilities. So I'm going to write here DG. So I'm interested in these 4 possibilities, right? I could have A or F on this transition, or D or G on this transition, and I'm looking for the minimal distance. So I'm not going to look here in the trellis because that's not going to give me enough information. What I need to look at from the trellis, of course, I see AF and DG. That was useful, so I'm going to be looking again at that. And for the A to A transition, it was A and F. And for the the A to B transition, it was D and G. So these are the 4 that I'm interested in. And so I look at these 4, and of course I can't make a mistake between A and F because they're green and green. So that's not those. It's between a green and a yellow, if you will, that I'm looking. So I look at the distance between this green and this yellow, or between A and D, I have this distance. Between A and G, I have this distance. Between D and F, of course, it's the same distance as D and G. And of course, here there's that. So there's 4 different distances in this case. Well, there are always 4 distances to examine. In this case, there's really 3 distances because we have the distance between A and D, which is, of course, quite large. And it's greater than the distance between, let's just say, A and G, or D and F. And that, of course, is bigger than the distance between G and F. So if I'm looking for the minimum distance, then the distance that I have to record for this branch metric is the distance between G and F, because these are the closest. So I look at the distance between G and F, and of course that's this distance, AB, AH, they're all the same. It's a distance of 2. So I'm going to write that for this part of the time 1, the distance, the final branch metric, is going to be 2. So this is the distance between the A to A and the A to B transition. The minimum distance between those 2 is 2. So now I have to look at the next transition, and I'm comparing the transition from A to A with the transition from B to C. So I said I was interested in the transition between B and C. So this transition and A to A, of course, those are the 2. So now let's call this one the green one. So I'm interested in, now I'm looking at the letters here, and it's symbol B or symbol E. And in the case of A, I'm interested in A and F again. So I guess A and F is always going to be key players there. So I look again at what are the distances now. And here I see one distance, here I see the same distance really, and then the distance here, and of course the distance here. So there are 4 distances, and the distances between A and E would be greater than the distance between B and F, which of course is greater than the distance between A and B, which would be just equal to the distance between F and E. And this distance, of course, is 2. So once again, I go down here, and I'll say the minimum distance is 2 for this transition as well. So now we're going to the next one, and in the last one, I'm going from state C to state A. So I'm going to go look at that part of the trellis. So for the C to A transition, we have it there, and again, it's A and it's F. So we have the same code words in this case. And the minimal distance in this case, well, clearly is going to be 0. Because, of course, if I did the distance from A to F would be the same as the distance from F to A, of course. But that's always greater than the distance from A to A or the distance from F to F. And this distance is just 0. So now I go down and I say the distance on this transition is 0. So now I've gotten the path metrics at each one of the points, and it's time to the branch metrics. And now the path metric squared is equal to the square of each of the branch metrics. So 1 squared plus the second one plus the third one. Of course, when I was given these distances, they were already listed, as the square distances. So you can see they had the square there. So each one of these distances that I've recorded here is the squared distance. So the total would be equal to 2 plus 0 or equal to 4. So the distance for this path would be equal to the square root of 4 or equal to 2. And is that the minimum distance or the free distance? We don't know yet because we have to examine the other path. Now I do the exact same operation here. So I can reuse some of my information here because I've already examined the difference between these two paths, and that was a 2. And the path here I've already examined. This was the path 0. So this was the 0. Whoops. This was the 0. But this B to D and the D to C I haven't examined before. So the B to D we haven't done. So we'll start with that. B to D involves H and C. So H and C. And of course, we have A and F for our transition for A. So we start looking again at the different combinations, what the distances are between A and C, between H and F, between C and F, and between A and H. So we have basically 2 distances, the BC distance, the AC distance, which is equal to the HF distance, which is greater than the distance between AH and CF. Those two are the same. So I look down in my table and I say AH, that distance is 2. So I know that for this transition, I also get a 2 for the B to D transition. So the last one is D to C. So I'm going to go back up here and I'm going to look for the D to C transition, and the D to C transition is B and E. So now I go down to get my distances, and there's the distance here, of course here and here. So we've looked at this case previously. So it was the A to E case, which was greater than the B to F case, and the distance was greater than that between AB, but that was the same distance as between FE, which is this distance of 2. So we go back down and we put in a distance of 2. So now we've finished. We have all of our branch metrics. So once again, we found the branch metrics, and so we have to find the path metric, which is the sum of each of the branch metrics. And in this case, we have 2 plus 2 plus 2 plus 0, which gives us 6. So the path here is the square root of 6. So for the final part of the question, we're looking at comparing uncoded QPSK with the coded TCM QAM. And to find the gain, we're going to compare the performance of each of them. And for the TCM modulation, that means we're going to look at the free distance that we found. And of course, we have to normalize it with the average energy per symbol. When we go to the QPSK case, of course, we're using the traditional minimum distance because there's no coding. But again, we normalize it by what is the average energy per symbol. So now if we go back and we scroll back, and what did we get for, let's start with the QPSK system. For the QPSK system, we said that the minimum distance was the square root of 2, and the average energy per symbol was 2. So going back down, we would put dmin squared would be 2 because the dmin was square root of 2, and the average energy per symbol was 2. So let's scroll up and see what we had for TCM. And for TCM, of course, the distance was 2, and for the average energy per symbol, it was 3. So going back to do our calculation, we would find that dF was 2, so 2 squared is 4, and the average energy per symbol was 3. Therefore, the gain would be 10 log 10 of 4/3 divided by 2 divided by 2. So that's just log 10 log 10 of 4/3, which gives us 1.25 dB of gain for this particular coding example.